Let us dive into the world of geometric dimensioning and tolerancing, or GDT for short, and why we care. So why we care is that there are no perfect parts, as you know. So everything must have a tolerance. And we have two ways we can apply tolerances to our drawings. One is called coordinate tolerancing, which is the kind you're used to. The other is geometric tolerancing. Here's a drawing. This happens to be from a company up in Hillsboro with coordinate tolerancing in their title block and also geometric tolerancing. And you can see geometric tolerancing symbols on their drawing. In coordinate tolerancing, we put plus, minus, or limits dimensions on our parts. And you might want to think about, well, what is the worst case, the tightest fit for this thing? We could have the biggest pin could be 2 2/2000 diameter. The smallest hole could be 2 3/1000. So you could have a part with 2 3/1000 to 2 2/2000. You could have a clearance of 1/1000. And you might think, hey, that sounds okay. But what if the parts are not geometrically perfect? They're not straight, they're not perpendicular, they're not round. Here's another example, not a round part, but a flat part. When we put a dimension like this on our drawing, dimensions plus or minus 10/1000, we're envisioning that we're going to get a nice rectangular part. And it might be a little bit bigger or a little bit smaller, but it'll be rectangular. And here is the size of the tolerance zone around that part. Well, if that is the tolerance zone, what that means is that the surface of your part could land anywhere in that tolerance zone and still be an acceptable part. So if what you really want is a part with flat sides and parallel sides, regardless how big or how small it is within those tolerances, what you do is you leave those size tolerances there, but you add some tolerances for, this is a symbol for flatness, so this says make those two surfaces flat within 1/1000. This is the symbol for parallelism, so this says make this top surface parallel to surface A within 2/1000. Now you've got a flat part. Geometric tolerancing is made of a set of symbols, and they look like this, and they define what these tolerance zones are going to be like. And it's based on ASME Y14.5, and you're familiar with this standard already because we use this for dimensioning. It turns out that only the first chapter of this standard actually has to do with dimensioning, and all the rest of the chapters have to do with geometric tolerancing. And here you can see on the cover there's some GDT symbols, which we're going to learn how to read. The heart of this system is that you tolerance the part based on how it functions. And you use gauges that are based on how it functions, and it really allows interchangeable parts. Believe it or not, parts with GDT actually have lower cost than other parts because you actually can have larger tolerances. We'll see why as we go along. And you can wind up accepting more good parts and rejecting fewer good parts. Functional gauging is like this. So here's a part that's going to have 3 holes, and here's a geometric tolerance that says the position of those holes should be within this tolerance zone. So to inspect this part, rather than get calipers and gauges and all kinds of stuff and tediously measure everything, our inspector makes a functional gauge, and it looks like this for this part. And we'll learn how to figure out what size to make these gauge pins. Well, then your inspector takes this part, drops it over this gauge, which is a kind of a mimic of the mating part that this thing is actually going to fit with. So here's the functional gauge. You drop it on, either it works or it doesn't, and that's it. This geometric tolerancing system uses two kinds of elements. One is a set of datums, and a datum is surfaces or lines or points, places from which you take your measurement. And then it has these tolerances, and we use these things called feature control frames that define the tolerance zones. Well, there are several advantages of using GDT, and here they are. We'll go through these one at a time. First, you can use cylindrical tolerance zones. Now, when you're using coordinate tolerancing, the old plus minus or limits version, the tolerance zone, which is represented by this red colored square in there, the tolerance zone is square. And here's a close-up of the tolerance zone in this part with plus or minus tolerancing. So let's say you are locating the hole, and on the hole location you have a tolerance of plus or minus 3.5 thousandths, side to side and up and down. That means that your tolerance zone, looking close up at the zone here, is 3.5 thousandths side to side and up and down away from that theoretically perfect center point. Okay, so if you have a part that is, let's say, the center of your part that you actually made happens to be located diagonally away from the theoretically exact center, that would be a good part. And if you want to figure out where would that be, over 3.5 thousandths, up 3.5 thousandths, that whole center line for that part that you made is about 5 thousandths away from the whole center. However, if you had another part with a hole where it had a center line that was 5 thousandths away from the center, but it was off straight up and down, that part would be rejected because it's outside the tolerance zone. Well, GDT says that's kind of illogical. Why don't we just give these parts a circular tolerance zone? And if we are saying, okay, the whole center for an actual part that we made could be 5 thousandths away, let's just make the entire tolerance zone circular. We'll give it a radius of 5 thousandths, and that will be good. Now, if you were to use your geometry skills and figure out the area of a square and the area of a circle that would fit around that square, you would find out, surprisingly, that the circle actually has 57% more area than the square that fits inside it. In other words, for the same size tolerance zone, if you use a circular tolerance zone, you can accept 57% more parts than if you used a square tolerance zone. A second advantage is that you get a bonus tolerance. So with a coordinate tolerance system with the plus or minus zone, this is the tolerance zone, that's it, that's all you get. With geometric tolerancing, over here on the right, this feature control frame says, locate the position of this hole within a tolerance zone that's 10 thousandths in diameter if you make the hole at maximum material condition, which means if you make the smallest hole. But if you make a hole that is within the size tolerance, but it's bigger, you get to have a bigger tolerance zone. And that makes sense. I wish we could hold up some parts for each other and look at them physically. But if you're fitting this block over some kind of mating peg, if you have a bigger hole on this block, you can have more slop side to side and up and down, and it will still mate over that peg. So it makes sense that you would be able to have a bonus tolerance. The third advantage of GDT is that you get unambiguous inspection instructions, and here's what that's talking about. Let's say you're using plus or minus tolerancing, and you've got a part with it's supposed to be rectangular and it's got 2 holes. And we know there are no perfect parts, so it's going to be not quite smooth and not quite square. When your inspector puts that part in his or her inspection equipment to measure the location of this hole, they might set the long side down flat and measure the hole off the precision square. The next shift, a different inspector might place the short end on the surface plate, press it up against the precision square, and measure the X dimension that way. Well, you might be able to imagine that those 2 inspectors are going to get 2 different readings on that hole location. And in fact, one of them might accept a part and one might reject a part, even though they're made about the same. What we do in GDT is we use datums. So here is a feature control frame. This says, locate the position of this hole within this tolerance zone, and A and B are telling them A comes first, so it says put surface A on that surface plate first. B comes second, so that says second, snug B up against the precision square. Now with this kind of tolerancing, every inspector is going to set up this inspection the same way. They'll put surface A down first, they'll put surface B up second, and everybody will measure it the same. So benefits also relate to the fact that GDT gives you parts with lower cost. Why? First of all, because we have a cylindrical tolerance zone, we can accept 57% more parts or reject 57% fewer. We can have bonus tolerances, so we can accept even more parts because we know they're going to work. And we can inspect our parts consistently, so we know they're going to work. So GDT is actually an advantage in manufacturing, and most manufacturing facilities do some kind of training in GDT so they know how to read your drawings. Our goal here will be to learn how to create those drawings.